All right, so I believe we had wrapped up high-res poly 2 resistors on last Friday. So now we are going to be moving along to poly capacitors. So capacitors can be formed by overlapping the poly 2 layer above the poly layer. And there are specific rules that go along with that, which we'll look at here in just a moment. I was nice enough to make myself a note. Page 31, section 11. So let's find that real quick. There we go. Layout rules for our poly 2 capacitors. This thing doesn't slide with my touch screen. I'm on the wrong page. Move this so I can make it a little smaller. All right, so we can see everything now. So one of the key things here that we have to pay attention to is that the poly 2 has to be smaller than the poly 1. Okay, so the poly 1 layer, which is physically below the poly 2 layer in our top-down view, is smaller, so that we're always going to have a larger bottom plate for our capacitor than we are going to have a top plate for our capacitor. And this is going to cause issues with parasitic capacitances. Okay, so we circle back around here. A very simplistic layout for a poly 2 capacitor might be something like this. So we would have our poly 1 layer, like so. There would be a run of metal, which is going to serve as our electrode. So this blue is metal 1. And then we would have contacts, which would allow the metal to make electrical contact with the poly layer. And then poly 2, which I think I did in red. Would have to be something like this. Actually, well, it doesn't really matter, but I'm going to extend this one further. And then we'll have another metal 1 thing over here, so that we have access to apply signals to our 2 different capacitor plates. And our cross-sectional view of this structure is going to look something like this. So here's our substrate. Our field oxide. Recall that this effectively is a thickness of T ox. Then we have our poly 1 plate. Here we have, draw this accurately. Our poly 2 plate here. As discussed in last class, the spacing between the poly 2 layer and the poly 1 layer is approximately also the oxide thickness between the poly 1 layer and the substrate. And then we'd have up here effectively is where our metal layer is going to live. And here's our context. Okay, so picture's a little bit busy, but we have an intended capacitor here between our poly 2 layer and our poly layer. And then we also have a parasitic capacitance here between our poly 1 layer and the substrate. And this is discounting the parasitic capacitances we are going to see between the metal layers and the substrate and things like that as well. Okay. So this parasitic, let's call it C poly sub, is the dominant parasitic formed between the poly layer when we're making a poly 2 capacitor. Okay. Now, depending on the size of our bottom plate, this parasitic capacitance can be close to, or at least on the scale of, the value of our designed capacitance. So, for example, let's say that we are going to calculate the capacitance of a poly 2 capacitor. If the poly 2 plate has dimensions of 20 lambda by 50 lambda for a C5 process. And then we want to know, how does the bottom plate parasitic capacitance compare to the intended capacitor? So we're going to make a couple of assumptions here. The first of which is that our poly 1 plate is going to be as small as it can physically be while still maintaining the proper design rules. Okay. So if our poly to poly 2 capacitor, if our poly 2 plate is 20 lambda by 50 lambda, then we would see that C poly 2 is going to be, I'm going to call Cox prime for this particular layer. And this is where we use our table. So on the table, the capacitance between poly and poly 2 is given as 893 attofarads per micron squared. I'm just going to tuck that in right here. 893 attofarad per micron squared. And then we're going to multiply that by the area of our plate, which is 20 lambda by 50 lambda. Putting in numbers, this looks like 893 attofarads, which is 10 to the minus 18 farads per micron squared, times 20 times 50, excuse me, times 0.3 microns quantity squared. Since 300 nanometers, the scaling feature for our C5 process is the same as 0.3 microns. And this comes out to be 80.37 femtofarads. So to get our C poly, the substrate value, we need to look at our design rules and figure out what the minimum size of our plate is going to be. So the minimum poly overlap, which is defined by section 11.3 here, says that we must extend, if we're looking at a submicron process, which is what the C5 is, we have to extend 5 lambdas in every direction. So we have to be 5 lambda to the left, 5 lambda to the right, 5 lambda to the bottom, 5 lambda to the top. So effectively, we just need to add 10 lambda to both dimensions to take this into account. So we're going to have a 30 lambda by 60 lambda bottom plate. Anything larger than that would still work for this particular poly to poly 2 capacitor. However, it would just result in a larger bottom plate capacitance, which is bad. So we're going to assume that this is what we're using. And reading our table this time, our capacitance per unit squared between our substrate and our poly layer is 86 attofarads per micron squared. Oops, went slightly too far. So plugging in these numbers, we have 86 attofarads per micron squared times 30 times 60 times 0.3 microns squared. And this comes out to be 13.93 femtofarads. So effectively, our parasitic capacitor is roughly 1/6 the size of our desired capacitance, which is a pretty large consideration here. Okay? So this is something that we need to be aware of. There's not a whole heck of a lot that we could actually do to mitigate this, though. The design rules effectively tell us how this is going to be. All right. So let's see. Those are our poly capacitors. The only other thing that I really want to say here is, typically speaking, the poly capacitors are formed by using the doped polysilicon. So you wouldn't use the high res poly layer for a capacitor. You want to be able to push charge and on and off of it pretty easily, so you don't want it to be too overly resistive. All right, so I have notes here regarding temperature coefficient, capacitance, and all that kind of good stuff, which we'll absolutely cover. But let's talk about metal layers now, and then we'll talk about that kind of stuff. So embedded here in our discussion of the metal layers, we are also going to be talking about two other layers, the contact layer and the via layers, okay? So in our hierarchy, if we were to draw out the cross-sectional view, down here is our substrate. And then embedded inside this oxide layer, we have our poly 1 layer. And then we also have our poly 2 layer. And I'm going to refer to this right here as what's called an ILD, or interlayer dielectric. Effectively, it's a fancy thing for saying it's an oxide. Okay. So on top of this first interlayer dielectric, we have our metal 1 layer. And I'm playing fast and loose with the sizes of these layers, and we'll define things a little bit better in a moment. Then we have another interlayer dielectric. And then we have our metal 2 layer. Interlayer dielectric. And then we have our metal 3 layer. And for a C5 process, we only have access to these 3 layers. So let's label this stuff metal 3. Metal 2. Metal 1. All right, so if we want to make contact from metal 1 to either of the polysilicon layers, we use what's called a contact. Okay. So contact is specifically for making contact from a metal connection down to something underneath a metal 1 layer, or specifically from metal 1 and down in the physical space. So metal 1 can directly contact poly 2, poly 1, and well, although that's really a bad idea, or an active or p active. Mainly poly, poly 2, and active regions. Okay. Then we have this guy right here, which provides contact from metal 2 to metal 1. This is a via. I believe I'd have to double check electric here. It's called via 1. And then this guy over here is via 2. It provides contact from metal layer 2 to metal layer 3. So when we're going from metal 1 down, we're dealing with contacts. When we're going from metal 1 up, we are dealing with vias. One thing that is actually pretty important though is that you cannot go from metal 1 directly to metal 3. You have to hit an intermediate metal 2 layer to go up higher, okay? Now, contacts and vias are literally the exact same thing. They are 2 lambda by 2 lambda by default, cannot make them larger than that. Tungsten plugs having a resistance of approximately 10 ohms. Okay. They effectively serve as a single point of contact between those 2 layers. So generally speaking, only having a single via or contact is a terrible idea. Why might this be a bad idea?
You only have one, then wouldn't that mean if you want to get to the lower levels, you'd have to use that one connection all the way down, bypass the intermediate layer?
So you can't use it to bypass the intermediate layers. The problem with only using a single point of connection is that if it fails, you no longer have access to those other regions of the chip. So if we look back here at the poly to poly 2 capacitors that I drew, I have 5 contacts from metal 1 to poly and 4 contacts from metal 1 to poly 2. Putting them in parallel like that means I no longer have a single point of failure that renders my chip inoperable. I now have multiple parallel paths that effectively do the exact same thing. A arguable added benefit of this is all of these are 10 ohm resistors effectively in parallel. So the more contacts I can put in, or the more vias that I can put in, the smaller contact resistance that I have. Because typically speaking, if we're connecting from one metal to another metal, and the metal has resistance on the order of 0.1 ohms per square or lower, and we'll talk about that in a little bit, throwing a 10 ohm resistor in the mix is just going to increase ohmic losses. Whereas if you can put a bunch of contacts in parallel, you're lowering the amount of losses that are going to occur as you send a signal from the top surface of the chip down or vice versa. All right, so speaking of sending signals on and off of a chip, how do we do that? Well, if we're sending a signal from an external source, we have to utilize the metal 3 layer because it is the highest metal layer. And we have to form what's called a bonding pad, okay? A bonding pad is a macroscopic structure on these microscopic chips, okay? It's relatively large, okay? So a bonding pad has minimum dimensions of 72 microns by 72 microns, large enough to bond a small wire to that particular point on the circuit. That's why it's called a bonding pad. We literally use robots to solder wires to these very, very small pads, okay? Let's write down here. Bonding pads. All right, so there the SCMOS design rules are in the document, but we'll talk our way through them here really quickly. Effectively, we have a 72 micron by 72 micron square of metal 3. This is literally the only thing in our design rules that has a fixed physical dimension. It is not in terms of our scaling factor or anything like that. It is minimum of 72 microns by 72 microns, full stop, okay? Now, typically speaking, we also have what's called a passivation or overglass layer directly on top of it, okay? And so I'm going to do that in gray here. I'm going to call this overglass. And this dimension is actually, hold on, better way to do it would be this way. Minimum passivation opening is 60 microns in either direction, okay? So let's talk about this overglass layer here very briefly. Effectively, what the overglass layer does is it holds down the metal 3 layer, okay? So this interlayer dielectric right here is effectively the overglass layer. It is an oxide that is literally grown over the top, and then a hole is cut out that allows you to actually probe those metallic points on the chip. If you had the metal layer fully exposed, you could get mechanical deformation of your bod pads and things like that. They could literally float off and detach. So this physically holds it down to the surface to maintain contact with the underlying layers and all that kind of good stuff. That's what the overglass or passivation layer. Exactly right. So that's a hole inside the passivation layer, because without that hole there, you can't actually bond a wire to that metal 3 layer. You'd be sticking it to an insulator and not making electrical contact.
Passivation.
Oh, say literally just a different word for the overglass layer. They're the exact same thing. I honestly don't know why they call it passivation, but yeah. Overglass makes more sense to me because you're putting glass over the metal 3 layer. So. All right. All right, let's keep going. So I think I've covered bond pads enough, all that kind of stuff. We talked about using parallel vias and parallel contacts, place as many as possible, putting them all in parallel lowers the overall resistance. And then we'll get into, okay. Moving on to bigger and better things now. Covered the basics, resistance of metal layers, and then some of the things that we need to pay attention to there. So it doesn't look like I have any specific resistance values here in my table that I gave to you guys. So generally speaking, the resistance of these metal layers is somewhere on the ballpark of 0.1 ohms per meter. Technically, the resistances between the different metal layers are slightly different, but they're all somewhere in that area. And the reason why those sheet resistances are slightly different is because the thicknesses of those metal layers are slightly different. So as we increase in height vertically, the metals get thicker and thicker and thicker, okay? But like I said, generally speaking, R square or metal we'll treat as approximately 0.1 ohms per square. So if we had a wire made of metal, where the wire was 3 lambda wide and 3,000 lambda long, what would the resistance of this wire be? That's pretty straightforward. We know that we're going to have 1,000 squares, right? R squared metal times the length over the width is going to look like 100 ohms here. Nothing particularly big there. Now, this metal is above the substrate. So it also forms a capacitance. How would we figure out what that capacitance would be? Well, that's why we have our table. So let's look at what the capacitance of this wire is going to look like, where this is from the metal 1 layer to the substrate, okay? So we're actually going to have to use both the bottom section of this table and the top section of the table. In our poly to poly 2 capacitor, we only had to use the top section because there wasn't data provided for the specific thing that we're going to be looking at here. So what we're about to show you, I'm going to draw a little picture here of just the end of the thing. So we have this is our substrate. We have that initial interlayer dielectric. And then we have our metal 1 layer. We have a capacitance formed between the bottom of the metal 1 layer, right, where we have effectively, let's use light pink. Nice, well-behaved electric field lines being oriented directly down. That's giving us our area capacitance. So the mathematical model for a parallel plate capacitor, epsilon A over D, is actually derived for infinitely large plates. We don't have infinitely large plates here, and our distance is large enough to where the fringe capacitance is also going to come into play. So effectively, the edges contribute to the capacitance as well, which is all what this bottom last 4 things on our table are about. So we are going to have a contribution from the area and the fringe here that we need to take into account. So using our table with the metal 1 layer in mind, we are going to have 28 attofarads per micron squared times 3 times 3,000 times 0.3 microns squared. So this bit right here is our C area term. And then for our fringe, look at the table if you have it. What are the units? The per micron thing is what's important here. So what do you think that implies? Right, but it's actually, so the fringe extends from the boundary of the plate. So that means we're going to use the perimeter of the plate multiplied by that capacitance per unit length in order to figure out what the fringe contribution is going to be. Because the fringe contribution only arises because of the edges. Does that make sense? Yeah. So in this case, as Sam pointed out, our constant here is 51 attofarads per micron. And then our perimeter is going to be 6,006 lambda. And 6,006 times 0.3 microns. I'm just going to make a quick note here. Perimeter. And then this whole thing right here represents our fringe. And performing this calculation, we get 69.5268 femtofarads, where a large portion of that is actually coming from the fringe capacitance because we have a long skinny wire. So the area isn't particularly large, but because we have so long of a run, we get that particular value. So what's the delay time for this thing going to be? 0.35 times R times C as a reasonable estimate, right? We are throwing away the n times n plus 1 and just saying that C squared times n times R squared times n is effectively the overall resistance times the overall capacitance. So our delay time for this, let's go down to the next page here, is 0.35 RC, which comes out to be 2.433 picoseconds. Now, let's calculate our intrinsic propagation delay. So when we did this for an N-well resistor, our intrinsic propagation delay was much, much shorter than the actual delay time of the RC network, right? Here, our intrinsic propagation delay, which is the square root of epsilon R over C, the speed of light in a vacuum, times L, the length of our wire, comes out to be approximately 6 seconds, where we're taking epsilon R to be the relative permittivity of silicon dioxide, which is the material that forms the interlayer dielectric. So our delay time based on our R and C value is actually shorter than our intrinsic delay time that we can possibly achieve to propagate a signal down a transmission line that is being separated by the silicon dioxide, which means the true delay time for this RC network is closer to the intrinsic delay. Okay, that's something that we're going to see a lot for our metal layers, and it comes from the fact that our metal layers can be extremely long but have very low resistance values. All right, so effectively, we don't have to worry about the delay time generated by the RC network using metal runs. We do at times have to worry about the resistive losses and things like that, which we can largely mitigate by just making our metal runs wider, right? So if we need to get a signal 3,000 lambda away, we can make this half as resistive by doubling the width and so forth. All right, so absolutely. So we're about to talk about reasons why we might want to do that. The first of which, we're going to talk about the concept of electromigration, which this is related to, let's call it current carrying limitations. So in the macro scale, the current carrying limitation of a wire is defined by what's called the ampacity. Okay. And the ampacity actually has a lot to do, not necessarily with the wire itself, as not burning out the insulation that's protecting the wire. So if you carry too large of a current, effectively, it'll heat up too much, which may melt the insulation layer, causing short circuits and burning your house down or whatever. These wires in a CMOS device don't have insulation particularly, unless we bury them inside of an oxide layer or anything like that. But what we have to worry about is effectively we're making runs so physically small that we can melt the layer, the metal itself, by carrying too much current. And in doing so, we can cause the stretch of wire, stretch of metal, to physically move or deform. And this is called electromigration. So this is a process, or I guess a better thing would be a phenomenon. Phenomenon in which metal layers physically move or deform after carrying too much current. So metals used in a standard CMOS process have a metal migration threshold current density. So J aluminum is equal to 1 milliamp per micron. I'm going to write that down. So effectively, if we have a 1 micron wide wire, any current above 1 milliamp, we should expect our wire to experience mechanical deformation. So if we need to pass large currents through our device, we have to make our wires wider, which is what we were literally just talking about a moment ago. So let's estimate the maximum current a metal wire, which is 3 lambda wide, and a bonding pad, which has its minimum dimensions of 72 micron by 72 micron, can carry in a C5 process. All right. So So for the wire, this is fairly straightforward. We have our threshold current density multiplied by the width, 1 milliamp per micron times 3 times 0.3 microns is 0.9 milliamp. For our bonding pad, doesn't particularly matter if we use the width or the length since they're the same. If we have a square bonding pad, this is obviously going to come out to 72 milliamps, right? I have a little blurb here regarding calculating the voltage drop over a long run of wire, but that's fairly straightforward because if we know the current flowing through the wire and the length of the wire and the sheet resistance of the wire, that's literally baby stuff, so I'm not going to worry about that too much. The note here just says, in general, metal 3 is thicker than metal 2, which is thicker than metal 1. So for signals where you can't afford ohmic losses, use higher metal layers due to their lower sheet resistances, which again, we already mentioned. All right. Yes.
Is the third roller always a one?
For the on-semi C5 process, yes. But in general, bonding pads are formed on the highest metal layer. So if you have a process in which you have access to 7 metal layers, your bonding pads will be formed on metal 7. It has to be the topmost layer. You cannot effectively embed your bonding pads down at a lower layer and then try to make a deep channel through several layers of silicon dioxide or whatever type of insulation you have. It needs to be as close to the surface as possible. And then you would use vias and contacts to get your signals lower down to the actual transistors or whatever you have in the substrate. Sure. Right.
But we have to get the metals of the layers.
That's correct. So let's draw a picture of what I mean. So this is, so let's say that we were, this is our substrate. Why the S isn't showing up. And our target here, for whatever reason, is to connect to this and active thing, okay? Here's our first interlayer dielectric where the poly and poly 2 layers exist. We don't have to go through those two, okay? But if we wanted to, here's our second interlayer, etc. Okay. So this is where metal 2, or excuse me, metal 1 exists. This is where metal 2, and then up here is our big bonding pad or whatever. We would have to go from metal 3 to metal 2 using contacts, or excuse me, using vias, metal 2 to metal 1 using vias, and then metal 1 to the active layer using contacts.
Okay, so we're not making an assumption that there are metals between the layer.
Right, there has to be.
Okay. Just because of
Yeah.
manufacturing process?
Yeah.
Okay.
Yeah, I mean, like, you're 100% correct there. That is a constraint of the manufacturing process itself.
Make the bead is that.
Exactly right. You can't sputter the tungsten plugs accurately that deep, yeah. So like typically speaking, you would have, your bonding pad is this big, 72 microns by 72 microns. You can run up a smaller physical dimension piece of metal to touch that, as long as it's large enough to carry the current that you're expecting to carry. The bonding pad's dimensions are purely because you need to be able to physically bond a wire to that. Very, very thin wire on the order of 50 microns or smaller in diameter, but it is an actual wire that's going to go off to the pins that you have access to when you plug this into a breadboard or something like that, okay? So it needs to have a fairly large size, but then there's a metal run, and there's typically what's called, let me find it in my notes so I don't misspeak here. Electrostatic discharge protection. That now seems like as good a time as any to talk about that since I've turned this page to the notes, okay? So this is one of those kind of general structures, all right? Electrostatic discharge protection. All right, so in modern, that looks too much like modem for my comfort. CMOS processes. The gate outside is extremely thin, on the order of a few angstroms. I'm misspelling extremely, excuse me. And thus, vulnerable to damage from electrostatic discharge. What does damage to electrostatic discharge mean? Anybody have any thoughts? Yeah, but I mean, what would be an example of electrostatic discharge?
Electrostatic electricity.
There you go. Why do any IC that you buy, why does it come in a static bag? Because of this.
It's basically the reason that almost all of the. There was another console around at the same time as the Atari and television time. They didn't put proper electrostatic shielding on. It's one of the reasons you can't find any today.
I don't know. I'm just trying to think.
ColecoVision.
Okay.
ColecoVision. They did make many of them, and part of the reason not around today is almost none of them had electrostatic discharge shields for the controller ports in the age of shag carpet.
Yeah. So you would literally,
Like, yeah,
fry electronics, all this kind of stuff. Yeah. So if you buy any type of, modern computer memory, video cards, even, yeah, all of that kind of stuff. If it has any type of sensitive electronics, it's coming with some sort of electrostatic discharge protection, like it's coming in a bag effectively to make sure that static electricity doesn't damage it in transit. And then there's also structures in place within the integrated circuit. These structures are diodes. That's it. Simple diodes to prevent current from going the wrong direction and blowing stuff out, okay? So the general structure would look something like this. here we have our bonding pad, or this is what we are trying to achieve effectively. And then we have this node right here, where we have a diode between VDD and this port. Let's call this V1. And then we have another diode between that same port and ground. And then here is our transistor. That's the wrong arrow. Or it's on the wrong terminal if I want it to be an NMOS, and it's on the wrong direction if I wanted it to be PMOS. I have to fix that. But this transistor effectively just represents the electronics that we are trying to protect. Okay. So if a large voltage is applied to the bonding pad, D1 clamps our gate voltage to somewhere in the ballpark of 5.7 volts, where we're assuming that our diode has an on voltage of around 0.7 volts, and any excess charge is sent to the power supply. If a large negative voltage is applied to the bonding pad, D2 clamps the gate voltage to approximately negative 0.7 volts, and all of our excess charge is set to ground. So effectively, no excess charge ever actually reaches our transistor. Everything is shorted up to the power supply or down to the ground. So how do we implement something like this? Well, we have our bonding pad here. On our metal 3-layer. And then imagine we have multiple vias getting us down to the lower levels. Here's our metal 1. We're going to make contact here. And then let's see, there's some gray here, sorry. So this thing right here, this is our N select layer. And then on the opposite side, we're going to have something like this. Where this guy over here is our P select, and this is to ground. Okay. So effectively, we have N active material abutted up next to P active material. We have created a PN junction where both sides are doped pretty heavily. So we have a nice, pretty intentional diode, right? And then we would do the exact same thing on the other side, except we would have this is why I desperately need to convert these all to PowerPoints at some point. Yes. So on this side, we have the P on top and on bottom or whatever, and then to VDD, and then that middle path is actually just to the chip we're trying to protect or whatever. So we're just sending extra charge to either our ground rail, which is going to encompass the chip at a lower metal level, or our VDD supply rail, which is also going to be lower on the chip at a metal level. And actually, I have something written here, so I want to make sure that I include it. This guy right here needs to be sitting in and end well for it to work correctly. All right. All right. Let's stop here for today so I can go grab lunch before senior design. We're going to pick things up by talking about metal capacitors and schemes to make them not as good as poly to poly capacitor or poly to poly 2 capacitors, but as good as we can make them, just because sometimes we'll use metal capacitors. And at a minimum, we need to worry about the parasitic capacitances between different metal layers. And we're pretty close to being wrapped up with everything that should be covered for exam 1. I think the only other thing that we have yet to talk about here would be dealing with voltage coefficient of resistance, temperature coefficient of resistance, voltage coefficient of capacitance, temperature coefficient of capacitance. So we should wrap up effectively all exam 1 material by the end of class tomorrow or very early on Friday. And then we'll talk about slightly less boring stuff, matching of elements, and then we'll move on to active components and transistors and schemes for all that kind of good stuff. And then we're going to start doing math. Yay. All right. Is that the max? Oh, no, it's not the.
No, it's the new max. Yeah,
Okay.
it's the new max. We're definitely up.
That's probably going to be about as many as we're going to get to. Within the next 2 weeks, it's just going to be black. Just writing good old stuff down. Or 99% black.